Hello viewers, in this session we will discuss yet another version of Cauchy's theorem like we said last time. So far we have Cauchy's theorem on a rectangle and then Cauchy's theorem for a disk. So today we are going to see that if we have two simple closed curves one inside other, okay, I will make those terms more concrete. So, if one is inside the other and both are oriented in the positive sense, then the integration of f of an analytic function f on one of them is equal to the integration over the other. Okay. So, I will make the statement more precise. So, here is Cauchy's theorem version 3. From here on in this course, the curves that we are going to consider are always going to be contours unless mentioned otherwise. So, please take a note of this. So, in order to make some preparation for stating this theorem, let us start with some recollection of properties of a simple closed curve. Okay. So, we will call the trace of a simple closed curve as a simple closed curve. Okay. So, what that means is I will constantly keep confusing the curve with its trace when there is no much ambiguity. Okay. And having said this, the first fact we will need is or the property of a simple closed curve that we will need is that a simple closed curve separates or its trace in the complex plane separates the plane into two components, two components, i.e. The complement of a simple closed curve, I will say SCC for short, a simple closed curve in the complex plane is the disjoint union of two open connected sets. Or components. So, open connected sets are also called maximal open connected sets are also called components. Since they are disjoint, these are called components. And this statement is called the Jordan curve theorem. So, for simple minded curves, this is reasonably easy to believe. So, for example, if you consider a circle in the complex plane, then it is clear to see that the complement of the circle is the disk inside the circle and the region outside the circle. But in general, for a simple closed curve, this statement needs a proof, and we are going to assume that this statement is true for a general simple closed curve. So, a simple minded example is like that is a simple closed curve or a trace of it. So, with some direction, let us say, then the complement of this curve is that portion, and then outside of that portion. So, this is region 1, region 2. So, 1 union 2, the disjoint union of this is the complement. So, if I call this gamma, is C minus gamma. In this case, where the simple closed curve separates the complex plane into two components, the curve is the boundary. What is also important is that the curve is the boundary, okay, of either component. One of these components is bounded. Okay, since the curve itself is bounded, one of the components, it's intuitively easy to believe is bounded, okay, and the other is unbounded. Okay, and this much we will take it on belief, okay, and we call the bounded component as the inside of the simple closed curve. Okay, let us name the curve, let us call it gamma, okay, and denote it by I of gamma. Okay. So, I of gamma is a region in the complex plane, it is an open connected set which is the bounded component corresponding to the simple closed curve gamma. Okay. And notice that I of gamma is defined only for a simple closed curve and not for a general curve. We call the unbounded component as the outside of gamma, okay, of the simple closed curve, okay, gamma, okay, and denoted by O of gamma. So, now we want to talk about orientation of a simple closed curve. Okay. So, the simple closed curve gamma is positively oriented. Okay. So, we are trying to define positively oriented if the points of I of gamma appear to the left when traveling along the trace of gamma, in the direction of the increasing parameter of gamma. Okay. So, recall that we said we gave a direction to gamma based on the increasing parameter value. So, if the direction of gamma is such that when one travels in the direction of gamma, the points on the inside for a simple closed curve fall on its left, then we say that the curve simple closed curve gamma is positively oriented. Okay. So, for example, if you consider a circle, unit circle, and then you consider the function cos t plus I sin t from 0 to pi, for example, to c gamma of t is cos t plus I sin t 0 less than or equal to t less than or equal to 2 pi, then you start here and the trace in the complex plane, it goes in the counterclockwise direction to the observer from the top of the plane, and then this region, the unit disk d equals set of all z such that the modulus of z is strictly less than 1, it becomes your inside of this gamma. Gamma is a simple closed curve and d is the inside, and the set S is the set of all z such that the modulus of z is strictly greater than 1, that is everything which is outside, becomes the outside of this curve. So, and then we call this curve positively oriented. Okay. So, notice that if gamma is positively oriented, then we defined a curve minus gamma, which traces gamma in the opposite direction. Okay. That is not positively oriented, we want to call that negatively oriented. Okay. We call gamma as negatively oriented. Okay. Of course, this has to be a simple closed curve. Okay. If minus gamma is positively oriented. Okay. So, that is positive and negative orientation for a simple closed curve. Okay. So, with these with this terminology, we are ready to state the third version of Cauchy's theorem. Okay. So, here is Cauchy's theorem. Okay. This version can also be called a deformation theorem. Okay. So, this can also be called as deformation theorem. A very simple version of what is usually called a deformation theorem. Okay. So, let gamma 1 and gamma 2 be two simple closed, okay, two positively oriented. I need this to be positively oriented simple closed curves. Okay. And I will also add piecewise smooth, since we are dealing with piecewise smooth curves only. Okay. Piecewise smooth simple closed curves. And let gamma 2 be contained in the inside of gamma 1. Okay. Also, let A denote the set, the trace of gamma 1 union the inside of gamma 1 intersection the outside of gamma 2, okay, union gamma 2 star. Okay. Union the trace of gamma 2. Okay. Let f be a function, a complex function of course, okay, which is analytic on an open set. Okay. Let us call that open set omega containing this set A. Okay. Then the conclusion is that the contour integral on gamma 1 of f of z dz, okay, is equal to the contour integral on gamma 2 f of z dz. Okay. So, so here is the schematic for this version of Cauchy's theorem. Okay. So, suppose you have some curve gamma 1, simple closed curve rather, gamma 1 oriented in the positive sense, okay, and then there is yet another curve gamma 2 not intersecting gamma 1 and also gamma 2 is completely contained inside gamma 1, okay, and here is gamma 2. Both of them are oriented in the positive sense. Okay. So, A, this A which appears in the statement of the theorem, okay, is essentially your region in between, so to say, according to the schematic. Okay. And it includes, A includes the trace of gamma 1 and gamma 2, okay, union region in between. Okay. The region in between is clearly the intersection of the inside of gamma 1 and the outside of gamma 2. Okay. So, that is your set A. Okay. So, what is important is independent of the schematic. Okay. So, A is compact it is a compact subset of the complex plane, okay, and that is very significant. Okay, and so here is the proof. Okay, there are some details that I will skip, but more or less this is the proof. So, I will assume that gamma 1 and gamma 2 are smooth. Okay, smooth simple closed curves. Okay, the proof for piecewise smooth simple closed curves can be given similarly. With some slight modification of the proof that I am going to give. Okay. So, first what we will use is the fact that A is a compact set. Okay. So, I have written it above, A is a compact subset of C. So, so by the epsilon neighborhood theorem, okay, there exists an epsilon positive. Okay. So, recall the epsilon neighborhood theorem, it tells that if a compact set is contained in an open set, then there is an epsilon neighborhood of this compact set, okay, which is contained in the open set. Okay. So, here we have a situation where A is contained in the domain of analyticity of the function f, which is an open set omega, okay, and then we can use the epsilon neighborhood theorem. Okay. So, A is a compact subset of C. So, there exists an epsilon positive such that A is contained, okay, A is contained in the union of the epsilon balls, where the union is over all points contained in A, okay, and this is in turn contained in the set under question, the open set under question omega. Okay. So, now what we will do is we will consider the intersection of a tiling of the complex plane with this set A, this compact set A. Okay. So, tiling is essentially, you imagine that the complex plane is divided into square tiles whose edges are parallel to the x and y axis, or the real and imaginary axis. Okay. So, so you imagine a grid. So, consider a tiling of the complex plane by squares of side, okay, by squares whose sides are parallel to the coordinate axis, or the real and imaginary axis. Okay, of side. Okay, so, the squares have a side length s, which is strictly less than epsilon by square root 2. We will see why this choice is important. Okay. So, what you have is, here is the compact set A, okay, schematically, and then you have tiled the whole of the complex plane, okay, using squares whose side length is s, which is strictly less than epsilon over root 2. It does not matter how small s you pick, okay, as long as, of course, it should be positive, it is the length. Okay. So, so you consider such a tiling, okay, and consider its intersection with A. Consider the intersection of this tiling with A. Okay, we are going to use the structure of this tiling to prove the theorem. Okay. So, the structure is essentially, there are squares, okay, and then there are portions of the squares when the curve, the boundary of A intersects the square tile. Okay. So, the intersection of a square tile with A, it can be 1 the whole of square tile such that square tile is contained in the interior of A. The containment of the square tile in the interior of A is important. The whole of the square tile could intersect A with it intersecting the boundary as well. So, we will separate that one case. Okay. So, the whole of the square tile such that it is contained in the interior, call such a tile a normal tile. It could be a portion, a compact portion of the square tile of a square tile, whose area is strictly less than the area of the square. And call such a portion of a tile a special tile. Now, a special tile could really be disconnected, in the sense it might have few portions or not just one compact piece. So, we will allow for that, and we will still call all those portions for a given square tile as a special tile. But notice that the number of pieces which A can split this square tile into has to be finite, because we are dealing with two compact sets, intersection of two compact sets, one is A and the other is the square tile. So, now let us denote the boundary of A by dou A. Notice that the boundary of A is nothing but gamma 1 star union gamma 2 star. That is the boundary of A. And now, special tile is possible when a square tile intersects the boundary of A. It is only possible when a square tile intersects boundary of A. A square tile is either completely in the exterior of A, or it is in the interior of A, or it could be that it intersects the boundary of A. We want to call a square tile still a normal tile when the intersection with the boundary does not take up any area of the square tile itself. And now, let us orient the boundaries of these tiles, both normal and special, in the positive sense. So, for a normal tile it is easy, you just consider the counterclockwise orientation of the boundary of the square. But for a special tile, I just mentioned that the number of pieces or the number of components of the boundary could be more than one. Nevertheless, each of them we will orient in the counterclockwise sense. So, after having done that, we notice that for a square tile, for a normal square tile, okay, let us call it capital S, okay, contained in A, in the interior of A. Okay. S is clearly contained of course in omega, because A itself is completely contained in omega. Okay. The integration on the boundary of S oriented in the counterclockwise sense of f of z dz is clearly 0 by Cauchy's theorem for a rectangle. Okay. So, here that symbol stands for boundary of S oriented in the positive sense. Okay. So, once the integral is 0, actually the orientation does not matter, but we want to keep the positive orientation for reasons which will be evident shortly. Okay. So, the boundary of on the boundary of S, the contour integral of f is 0 by Cauchy's theorem for a rectangle. Okay. And for a special tile, okay, for a special tile, okay, T, let us call it T. So, actually T is possibly a union of finitely many compact pieces. Okay. Then for a special tile T contained in A, the boundary of T is a finite collection of positively oriented simple closed curves. Okay. And if x is a point which belongs to the boundary of T intersection boundary of A. Okay. Notice that I said that that a special tile is possible only when a square tile intersects the boundary of A. Okay. So, there is such a point x which is contained in the intersection of boundary of T with the boundary of A. Okay. Then that special tile T, okay, is completely contained in B x epsilon by the arrangement that the side of any square tile is at most epsilon by square root 2. Okay. So, since S is strictly less than since S is strictly less than epsilon by square root 2, what you have is you take x to be a point in the intersection. Okay, and then this is your epsilon ball. Okay. So, this is your epsilon. Okay. So, since S is strictly less than epsilon by root 2, okay, any 2 points contained in the square T, okay, have to be are at most square root 2 S apart. Okay. So, they are at most epsilon apart. Okay. So, any 2 points, the distance between any 2 points y 1 comma y 2 is at most root 2 S for any 2 points S 1 or y 1 comma y 2 belonging to a square tile. Okay. And by arrangement S is strictly less than epsilon by root 2. So, this is strictly less than epsilon. Okay. So, if you consider an epsilon ball which is around a point which is contained in the square tile, of course, your whole square is contained in that epsilon ball. Okay. So, that schematic should convince you. Okay. So, your T is contained in this B x epsilon. Okay. So, as a consequence, so by so that by Cauchy's theorem for a disk, for a disk, that was version 2 we saw last time. For a disk, the integration on the boundary of T oriented in the positive sense, of f of z dz is equal to 0. Actually, this integration is possibly a finite sum of few integrals which are on the boundaries component boundaries of boundary of T. Now, we consider so whether you take a normal tile or whether you take a special tile, the integration on the boundary, the contour integration on the boundary oriented in the positive sense of f is equal to 0 by two different versions of Cauchy's theorem. So, now you consider the summation of the contour integral on the boundary of a tile T of f of z dz, where the summation runs over all square tiles, all special and normal tiles T. So, you consider the collection of all normal and special tiles, these have to be finite, because you are considering the intersection of a compact set A with these square tiles. So, there are only finitely many tiles like this. So, you consider the finite sum of these integrals over the boundary of T oriented in the counterclockwise sense, in the positive sense. And so, and then by either of above, you are actually adding a bunch of zeros. So, this is 0 by above, by the Cauchy's theorem version 1 and Cauchy's theorem version 1 for normal tiles and Cauchy's theorem version 2 for a disk for the special tiles. Now, this is important. Now, this equation is important. We will analyze the LHS. So, on LHS, on the left hand side of 1, let us call this 1. We will make the following observations. Every side of a normal tile, normal square tile, appears twice with opposite orientation. So, that is clear, because if you have a square tile, normal square tile, which is completely contained in the interior of the region A. So, maybe that is the other curve gamma 2. Then there is an adjoining square which shares that side. So, if you consider one side of a normal tile, any side of the normal tile, it is completely contained in the interior of A. So, so that side is common to yet another square which could be possibly a special tile, but that side is shared by some other tile. So, each of these sides which are completely contained in the interior are shared by two tiles, and then one of them will have the orientation in one direction, and the other will have the orientation on that side in the opposite direction, because both these tiles are oriented in the positive sense. So, when you consider a side of a normal square tile, then that appears twice in the integration, one for this tile and one for the other tile. So, that is one observation, and the second observation is that in the special tiles, every side or portion of the side of the square tile appears twice again. With opposite orientation. Okay. So, if like I mentioned in the earlier case in observation 1, if you have a side of a special tile, does not matter normal or special. Okay. If you have a side which is completely contained in the interior of A, then the integration of f occurs twice on that side with opposite orientations in equation 1. Okay. So, now if you have a portion of a square tile. Okay. So, for example, here is a square tile whose portion, okay, this is the portion. I will probably use a highlighter to show that portion. Okay. So, only a portion of it is present in the interior of A, or is present inside gamma 1. Okay. And in that event, that is also shared with an adjacent tile. Okay. So, that portion of the side of the square is shared with the adjacent square. Okay. So, and it is exactly that portion which is shared and not more. Okay. So, so the second observation holds. Okay. And now, there is a third observation that I make. Okay. So, in special tiles, okay, portions of gamma 1 appear, okay, and only once with the same orientation as gamma 1, okay, of gamma 1. Okay. Not only that, okay, also every point of gamma 1 appears in, okay, appears as the boundary, okay, or appears in the boundary of some special tile. Okay, either of these are clear. So, in the picture I drew here, you notice that here is gamma 1 oriented in that positive sense. Okay. So, that appears only once in a special tile, okay, because I mean there is no adjoining square tile containing the boundary as gamma 1. Okay. So, here is the special tile. In this example picture or in the schematic, gamma 1 only appears for this one. Okay, and then there is no other square tile sharing that portion of gamma 1. Okay. And also, since we are tiling all of the complex plane, it is clear that gamma, each point of gamma 1 has to appear in some square tile, it has to fall in some square tile. Okay. And 4, yeah, also notice that when you orient these special tiles in the positive sense, that tallies with the orientation of gamma 1. Okay. And there is a fourth observation, that portion of gamma 2 appear, okay, once with opposite orientation of gamma 2, and all portions or all points of gamma 2 star. So, here also as I said, this should be gamma 1 star actually in the third observation. Okay. So, all points of gamma 2 star appear in some special tile. Okay. So, portions of gamma 2 appear once with opposite orientation of gamma 2 in special tiles actually. Okay. So, if you have a tile intersecting gamma 2, which is the inner curve, okay, then you see that here is the portion, okay, hashed portion, and that intersects gamma 2, and when you orient the special tile in the positive sense, it picks up the opposite orientation to gamma 2. Gamma 2 is oriented in this sense. Okay. So, this is the fourth observation, okay. And these 4 observations lead us to conclude the following. Okay. So, the integration along sides of squares, okay, whether partial or full sides, it does not matter. The integration along sides of squares, okay, cancel each other. When the integration on the LHS includes a portion of or complete side of square, then it does so twice with opposite orientation. Okay. So, they cancel each other. Okay. And when you have these curves gamma 1 or gamma 2 or the trace of them actually appearing in the integration, the portions of gamma 1 are with positive orientation and the portions of gamma 2 are with negative orientation. And we also notice that each point of gamma 1 star and gamma 2 star participate in the integration on the LHS of the equation 1. Okay. So, with these observations we see that the LHS, okay, boils down to LHS of 1 is actually equal to the integration on gamma 1 after rearrangement, because portions of gamma 1 could be here and there in the integration. Okay. So, after rearrangement this is equal to the integration on gamma 1 of f of z dz, okay, plus the integration on the negative of gamma 2 f of z dz. Okay. And the right hand side of course is 0. Okay. And when you have all these sides of squares, the integration cancels. Okay. So, as a result we have that the contour integral on gamma 1 of f of z dz is equal to the contour integral on gamma 2 of f of z dz. Okay. And that is proof for the smooth version at least. Okay. And that completes the proof of Cauchy's theorem. We will see quick applications of this version of Cauchy's theorem. It is very useful. Okay. So, for example, let gamma of t be a circle of radius 39, does not matter, a very large radius, okay, centered at I, okay, 0 less than or equal to t less than or equal to 2 pi. Okay. Let gamma be that simple closed curve. Okay. Then find the integration, the contour integration on gamma of 1 by z dz. Okay. Now, if you start parameterizing if you start evaluating this integral by using the parameterization, it becomes very complicated. Okay. So, you have 0 to 2 pi this integral I, okay, let me call it I is equal to integration from 0 to 2 pi of 1 by I plus 39 e power I t times 39 I e power I t dt, which is dz. Okay. So, 1 by z dz. Okay. And you see that this integral is not easy to tackle. You have 0 to 2 pi cosine t plus I sin t divided by 39 cosine t plus I times 39 sin t plus 1 dt. Okay. So, it looks rather daunting, okay, but if you use the deformation theorem or the Cauchy's theorem, the version we just proved, you can see that here is I, okay, and you take a very large circle centered at I, okay, and if the interior contains the point 0, okay, so clearly the interior of this curve gamma contains 0, okay, then you look at the unit circle and we already know by the fundamental integral that 1 by z dz on the unit circle. Okay. So, gamma 0 1, let us call it, let us have a notation for unit circle, let us just call it C rather, okay, oriented in the positive sense. Okay. So, we know that if that is the unit circle, 1 by z dz on C gives us 2 pi I. Okay, this we computed, that is the fundamental integral. Okay. So, by Cauchy's theorem, okay, we see that this circle acts like gamma 1, okay, and this C acts like gamma 2, and C is completely contained in the interior of gamma 1. Okay. So, by the above theorem, by the above version of Cauchy's theorem, okay, we immediately see that the integration on gamma 1 of 1 by z dz is equal to the integration on C, okay, or actually gamma integration on gamma of 1 by z dz is the same as the integration on C of 1 by z dz, which is 2 pi I. Okay. So, you do not have to compute that integral. Okay. So, that is an application of this. Okay. So, you could have really any complicated curve which contains 0 on the interior, 0 in the interior, okay, and as long as, well, and if 0 is in the interior of that simple closed curve, and if the simple closed curve is oriented in the positive sense, then there is a ball of some radius around 0 which is contained in the interior. Okay. So, if 0 belongs to the interior of gamma, here is gamma, okay, then B 0 r is contained in the interior of gamma, because interior is an open set, okay, and we know by the fundamental integral that C, okay, 0 r1 strictly less than r, okay. So, it is a circle of radius r1 around 0, okay, of 1 by z dz is 2 pi I by the fundamental integral that we calculated. Okay. So, from this we can conclude that the integration on gamma, which is oriented in the positive sense, of 1 by z dz is also 2 pi I, okay, by using the Cauchy's theorem, which we just saw. Okay. So, this is a simple application, okay, and this version of Cauchy's theorem is very useful in deriving Cauchy's integral formula, okay, which we will see next time.